we'll be doing the M4 final hackathon. So in this hackathon, we'll be creating a classifier model that will help us with the bank marketing dataset. So the dataset contains information about direct marketing campaigns run by a Portuguese bank, and our goal is to predict whether a client will subscribe to a term deposit or not. So the classifier is judged based on its receiver operating class characteristics area under the curve, basically the ROC-AUC, and our model's predictions and truths are uploaded onto Kaggle, which will give us a score. So this dataset has 37,211 samples, 16 features, and 1 target. The test set has 8,000 samples, 16 features, and no target. So we'll be using the training dataset only, and we'll only be using the test dataset for prediction purposes. So first of all, as you know, it's important to import all of the necessary libraries, such as NumPy, Pandas, Seaborn, etc. We will read in our training dataset, which was provided by Kaggle, and you can see over here what the dataset looks like. There's age, ID, job, education, etc. There's also we can see the data types and the nulls of each of the data types, and we can see there's no nulls. That means there's no need to get rid of the null values, and we can see the D types, which will help us in the future for encoding purposes. So let's read in the test dataset as well. Next, let's try doing some data exploration. So let's check for missing values, check for imbalance, and do a quick skew check. So there is no missing values, as we already discussed, but there does seem to be a little bit of skewness, as you can see over here. So first step is pre-processing. So now we have to do some pre-processing to make sure the data is well readable and well acceptable for our machine learning models. So first we need to drop the ID column, because the ID column adds unnecessary information to our model. Encode the categorical features like jobs, marital status, education, etc., because they are written in text strings and machine learning models do not understand text. And then log transform skewed features, such as balance, previous, and campaign. They have very high skew. So if the skew is bigger than 1, it's probably better to log transform and compress the outliers into a more normal data. And then we can also scale numeric features. We're using a standard scaler to ensure all features are on a similar scale, which helps with the logistic regression and meta learning in our stacking ensemble. So first of all, as you can see, we're dropping ID, and then we encode categorical columns, and then we use a label encoder method to do this, and then we're also log transforming our skewed numeric features. So first of all, we're also scaling the features using a standard scalar library. So to verify if the skew was reduced, we're using a check skew function. As you can see, this highlights the before skewness and this highlights the after. So for some of the variables such as balance, the previous skew was 8.2 and the later skew was negative 0.6, which is a much better difference. So as you can see, all of them, the skew was reduced drastically. So the step 3 is baseline model and stratified cross-validation. So we are creating a baseline model manually to check how the model performs and what kind of things we might need in the future. So for this baseline model, we're using a LightGBM. A LightGBM is a highly efficient gradient boosting framework. And instead of physically oversampling like using SMOTE, we are using the scale post-weight parameter, which mathematically penalizes the model heavier for missing the minority cases. And this is the mathematics of the scale POS weight. And we also make sure to run a 5-fold stratified CV cross-validation method for the LightGBM. This is important to ensure that there's no data leakages, and we did not draw a lucky train test split, because sometimes each split could have lucky variables that can give us the wrong impression. So this cross-validation method makes sure to validate it 5 times across 5 different folds. And as you can see, we got the different CV, we got the different ROC-AUC under the 5 different folds, and they're pretty much similar. So the mean ROC-AUC is 0.794, which is pretty high, with a standard deviation of 0.0068. So next, we're trying some model experimentation. To ensure we have the best foundational model before hyperparameter tuning, we will test multiple algorithms using the same 5-fold stratified cross-validation splits in our process data. X-scaled. It's important to keep using the X-scaled because this is the pre-processed data that we have. So now we're going to compare 4 different models. We're comparing a LightGBM, the one that we just made, an XGBoost, a random forest, and a logistic regression. This is the basic one. For every model, we make sure to pass class weight parameters, scale POS weight, and class weight equals balance to force the model to pay attention to our 12% minority class. So as you can see here, we define the models, we run the experiment, and then we display the results. And the results here show that LightGBM basically has the highest AUC RC compared to all the other different models that we have. So next step is to do some advanced feature selection, or what we call RFECV. So before tuning the hyperparameters, we need to ensure that our model is only learning from high signal data. To achieve this, we implement recursive feature elimination with cross-validation. So using our best baseline model, LightGBM, and our 5-fold stratified CV, RFECV recursively prunes the least important features. It evaluates the ROC-AUC at each step to make sure that the optimal subsets of features that maximizes the predicted power while discarding noise. So after setting up the RFECV wrapper, we plot it into a visual graph, and we can see over here that around 10 features, it adds the most amount of information, and around 14 feature, it actually maximizes. So after 14 features, the ROC-AUC actually goes down. This indicates that the 15th feature might be adding some unnecessary noise, so we're going to be dropping that in the future. So let's also implement the learning curve plots to see how well our model is fitting. So we tried that, and as you can see, the training ROC-AUC has been slightly decreasing, and the validation ROC-AUC has been increasing. However, our validation ROC seems to almost stagnate around this point at like 0.79-ish. This kind of indicates that there's overfitting. So the diagnosis is the ROC-AUC 0.89 and the validation ROC-AUC 0.79 at the maximum dataset. Conclusion is the model currently suffers from a high variance overfitting situation. It means that the model is analyzing overly complex and memorizing training noise. So the action plan is to improve the fit, closing the gap, while maximizing the validation RCAC. We will implement advanced hyperparameter tuning using a library called Optuna, and we will specifically target regularization parameters, L1 and L2 penalties, and min child samples, and max depth to constrain the tree growth and force better generalization. So step 6, we'll be using Bayesian hyperparameter tuning, which is an algorithm by Optuna. So using this, we'll be choosing our parameters and getting rid of some of the unnecessary parameters for our model. So after running Optuna, we can see over here we get the results. And what do the results mean? So to address overfitting identified in the learning curve, Optuna raised our light GBM model, raising the RCAC to around 0.799. This is a marginal improvement compared to our previous RCAC. So the optimal hyperparameters directly constrain the model complexity to improve generalization. Since we were over complex, now it's reducing the complexity using tree constraint, leaf regularization, and mathematical penalties. So step 7 is to test set processing and final Kaggle submission. So we generated the final Kaggle submission by using the testing dataset that was previously provided. The testing dataset was not used for our model purposes because it's a black box model, and we'll be using that to create predictions. But also it's important to remember to transform the testing dataset into the same way that we transform the training dataset, because it will not run the same way if we don't do that. And then we predict and export. So that export gave us our Kaggle submission, as you can see over here in the leaderboard. That was our first submission, which gave us a public score of 0.79, which is surprisingly high. Next, we tried to improve our model a bit more, phase 2, by doing some stacking ensemble methods. So this is where we decided maybe it's better to stack some other machine learning models to improve the accuracy, improve the ACRC. So next step, we tried tuning XGBoost. We used similar tuning methods such as Optuna to create an XGBoost model, and we did the same. The XGBoost had a slightly lower RCAUC, however, it had a shallower max depth. This meant that it could help us generalize better if combined with our light GVM. And then we also did the same with CatBoost. It also had a pretty high RCAUC, but still, it would probably be good to help let us generalize. So we tried creating a stacked ensemble method by combining these 3 models. So for each combination, we generated an out-of-fold prediction in a leak-free manner. Each base model predicts on folds it was never trained on, and logistic regression meta-learner then learns the optimal blend. So we did that, and we got a final stacked ensemble method that combined all 3 of the baseline, which gave us a RCAC of 0.8, which beat our basically lower RCAC. However, when we submitted this in Kaggle, it gave us a slightly lower public score of 0.792 compared to 0.793. This we assumed is mostly because of overfitting, because our stacked ensemble model definitely did better in the cross-validation metric, but it did worse in the outcome, so it overfit in our training dataset. So now we transition to weighted soft voting, because we realize it's overfitting, so we're trying to weight it and soften the complexity a little bit. We tried doing a weighted blend, resulted in a performance plateau, which gave us a stacking CV of 0.08 and a stacking LB of 0.79, and the weighted LB of 0.7925. So the diagnosis is, honestly, this branch-based method has reached a point that there's not much improvements to be made. So next phase, we tried being retrospective and trying to go to a new direction. Because light GVM works the best, there's no point to doing a stacked ensemble anymore, because it did not improve it anymore. So we tried tuning it in the full dataset instead of the CV. The full dataset also did not really improve our public score by much, as you can see over here. It's almost the same. So we basically gave up on this as well. And final step, we tried an H2O AutoML. So the H2O AutoML is a machine learning model that handles pipeline from beginning to end. It automatically chooses to encode the data the way it wants, and it automatically chooses the best models to create the best outcomes. It's important to transform the pandas frameworks into a H2O framework so the H2O model can actually read the data. So after doing that, after running the model, it actually gives us a leaderboard with the best possible models it found. I only let H2O run for 10 minutes. However, you could let it run for 50 minutes, an hour, 2 hours, and the more you let it run, the better the outcomes usually are. So the first 5 were mostly stacked ensembles with the AC of about 0.79. So the best CV we got from the stacked ensemble model was 0.797. And then we actually submitted that to our Kaggle, and in our public score, it actually did marginally, like super slightly worse. So we did not actually select this model. However, it turns out after the submission was completed, in the private score, it did slightly better than all the other models. The reason that all of the private score is slightly higher than the public score is because the public score relied on only 50% of the training data set, while the private score would actually try that on 100%. So overfitting issues would be exaggerated in the public score, while it would actually generalize better in the private score. Unfortunately, I did not select H2O as one of my selected models, so it was not selected in my final submission. So for my final submission, the first model was likely selected. But still, it got us to a position of 7, which is a pretty decent outcome for this hackathon. Final retrospection on this is we tried many different models. We tried 1, 2, 3, 4, 5 different models. Light GVM with the Optuna hyperparameter tuning was the best manual model, and H2O with the AutoML, even though the private score was lower, was the best in the public score. So why did So the conclusion is manual machine learning is actually pretty powerful because it performs as good as AutoML, which handles everything by itself. So understanding your data and diagnosing the problem is much more important than just letting computers handle everything by themselves. And it's also very important to understand the business decisions to be made, because understanding that can help us further improve our models. So next time, if I had to do this again, I would try engineering some features, such as creating different ratios and different weightages for different variables, because sometimes things like income and age don't process linearly. Like a 20-year-old with a $5,000 saving account is much more impressive than a 6-year-old with a $5,000 saving account. So maybe penalize the 6-year-old with the $5,000 account and maybe not penalize the other one. So those kind of things can definitely improve our outcomes later on. So thank you very much for listening.